In this lesson of our Automotive Air Conditioning course, we will analyze in detail the working pressures of the system and the fundamental components of the refrigeration circuit. Understanding how the pressures behave at each point of the system is essential to diagnose failures, correctly interpret gauge readings, and understand the heat transfer process inside the vehicle. This knowledge will allow you to identify symptoms of low performance, leaks, or overpressure in the system much more accurately. On the screen, we can see a basic automotive air conditioning circuit. This diagram represents the general operation of most modern systems. In later lessons, we will go deeper into existing variations, such as dual evaporator systems or those using electronic expansion valves, but essentially they all share the same principles and components. Next, we will see the four essential elements that make up the refrigeration circuit in an automobile and that work together to achieve the cooling of the air entering the cabin. Evaporator or internal coil. It is located inside the vehicle compartment, generally behind the dashboard or inside the airbox. Its function is to absorb the heat from the air passing through it, thanks to the cold refrigerant flowing inside. The fan or blower pushes ambient air through the coil, and as it loses heat, the air cools down before being distributed through the ventilation grills into the vehicle interior. The evaporator must remain clean and free of obstructions to ensure proper heat transfer and to prevent frost or excessive moisture from forming on the surface. Condenser or external coil. This component is located at the front of the vehicle, just in front of the engine radiator, taking advantage of the airflow generated by the vehicle's movement or by the electric fans. In the condenser, the hot refrigerant coming from the compressor releases its heat to the outside and changes from a gaseous state to a liquid state. Proper condenser operation depends on its cleanliness, adequate airflow, and ambient temperature. If the condenser is dirty or the fan does not operate correctly, the system pressure will rise and the cooling performance will decrease considerably. Expansion valve. This device is responsible for regulating the flow of refrigerant into the evaporator. It acts as a restriction that controls the exact amount of fluid entering the internal coil. By suddenly reducing the pressure, the refrigerant experiences a temperature drop and enters the evaporator as a mixture of liquid and vapor. The expansion valve may be mechanical or electronic depending on the system design, and its correct adjustment is fundamental to maintaining the balance between high and low pressures, preventing overheating or freezing in the evaporator. Compressor. This component is the heart of the system, as it drives and compresses the refrigerant to maintain continuous circulation. It operates through a pulley driven by the engine belt, or in some modern vehicles, through an electric system. The compressor draws in the low-pressure gas coming from the evaporator and compresses it to high pressure and high temperature before sending it to the condenser. Its proper operation is crucial since any damage internally, lack of lubrication, or leaks in its seals directly affect the overall efficiency of the air conditioning system. To understand it better, we can observe a pressure gauge designed for R134a, which allows us to visualize precisely how the pressure behaves at this stage of the cycle. The refrigerant reaches the evaporator mostly in a liquid state, and being at a low temperature, it absorbs the heat from the air that the blower pushes through the coil, thus producing the cooling of the vehicle's interior. Evaporator temperature. The evaporator must remain above 0 degrees Celsius or 32 degrees Fahrenheit to prevent frost or ice formation, a phenomenon caused by condensation and freezing of moisture in the air. Under normal operating conditions, especially when the engine is idling, the ideal evaporator temperature is 4 degrees Celsius or 39 degrees Fahrenheit. On the low-pressure gauge, we can determine the pressure corresponding to that temperature simply by locating 4 degrees Celsius or 39 degrees Fahrenheit on the R134a refrigerant scale and reading the resulting pressure value. In systems that use R1234y as a substitute for R134a, to obtain the ideal pressure, the same previous procedure must be followed, but the gauge must have the 1234y temperature scale. Remember that in the video description, you will find the link to access the evaluation of this lesson, where you can reinforce what you have learned and check your level of understanding. High pressure. As we mentioned, the system also operates with a high pressure corresponding to the compressor outlet toward the condenser. At this stage, the refrigerant arrives as superheated vapor, or 100% vapor, and must be cooled down until it returns to its liquid state. When the heat exchanger of the condenser works correctly, the temperature at the midpoint of the coil should be approximately 15 degrees Celsius or 27 degrees Fahrenheit higher than the ambient temperature. For example, if the ambient temperature is 35 degrees Celsius or 95 degrees Fahrenheit, the average temperature in the condenser will be around 50 degrees Celsius or 122 degrees Fahrenheit. With this information, we locate on the high pressure gauge, or red, the corresponding scale for R134a and determine the ideal working pressure. In systems that use R1234yf, the exact same procedure is carried out using the proper gauge for that refrigerant. Function of the expansion valve. When the refrigerant leaves the condenser, it does so in a liquid state since it has released the heat previously absorbed. However, it still retains high pressure. At this point, the expansion valve comes into play, whose main function is to reduce the refrigerant pressure by making it pass through an orifice or restriction of controlled size. This regulates the flow of refrigerant entering the evaporator, allowing the fluid in that section to be mostly in liquid form and partially in vapor form. Thanks to this condition, the refrigerant can absorb the heat from the air flowing through the evaporator, cooling it efficiently, and thus completing the refrigeration cycle of the automotive system. Remember again that in the video description, you will find the link to access the evaluation of this lesson, as well as additional information, support materials, and links to other complementary videos on YouTube. When the system is turned off, the compressor does not draw in or compress refrigerant. Therefore, there is no circulation in the system, and the high and low pressures equalize. In this state, the circuit pressure depends directly on the outside ambient temperature. For example, for an ambient temperature of 35 degrees Celsius or 95 degrees Fahrenheit, on the gauge corresponding to the R134a refrigerant, a specific equilibrium pressure is obtained, which reflects the resting state of the system. Similarly, for the R1234yf refrigerant, the pressure indicated on the gauge will be slightly different, although close, depending on its thermodynamic properties, always under the same ambient temperature conditions.